Welcome back. Today we're diving into a really core challenge, I think, in a lot of modern software. It's this constant fight between data integrity, making sure writes are safe, and data speed, getting reads out quickly.
It really is a fundamental tension, isn't it?
Hmm.
On one hand, you absolutely need reliability. Every change has to be solid, consistent, validated. That's your transactional side.
Right.
But on the other hand, users expect things now, instantly.
Yeah.
So the system has to cough up data super fast,
Mhm.
often under heavy load, purely optimized for reads.
And this is exactly where the, let's say, traditional approach, often built on the simple CR pattern, create, read, update, delete,
Mm.
really starts to fall apart at scale.
Mhm. Because CRE forces this single data model to serve two completely opposing masters. It's trying to be the complex validation engine and the super fast presentation layer all at once.
And that just doesn't work well, does it? Trying to make one thing do both jobs leads to bottlenecks. You cram all that intricate business logic for writes next to the high-speed needs for reads.
And you end up with a code base that gets brittle, really hard to maintain, and honestly prone to weird side effects as the system grows. It becomes, well, messy.
So how do we fix this kind of structural mess? Well, we introduce separation. Separation of concerns, but at the architectural level. Today, we're unpacking Command Query Responsibility Segregation, or CQRS.
Right.
The mission really is simple. CQRS tackles this conflict head-on by separating the job of changing things the commands from the job of retrieving things the queries. We're talking distinct pipelines, often even distinct data models.
It's definitely a strategic move to manage complexity. And, the underlying idea isn't entirely new. It's sort of a generalization of the command query separation principle, CQS, which Bertrand Meyer talked about way back.
CQS, right, I remember that.
Yeah, but CQS was more a rule at the method level. A
Mhm.
function should either change state, be a command, or return data, be a query, but never both in the same call.
Okay.
CQRS takes that clean principle and just scales it up, applies it across the whole system architecture. It's strategy, not just tactics.
That's a really important distinction. We're not just tidying up method signatures, we're building a fundamentally different structure, a dual pipeline architecture. So let's break that down. Starting with the right side. What exactly is a command in CQRS?
Okay, so a command is essentially an object that encapsulates a specific user intention or a business task. Think of it as a formal request, a message saying, please change the system state in this specific way.
And crucially, these are task-based, right? The sources really emphasize this.
Exactly. They should be descriptive of the task, like book hotel room command, not some low-level database operation like set reservation status reserved. That abstraction is key.
Why is that distinction so vital? Book hotel room versus set status.
Because the command defines the intent, not the how. It's typically a void returning message. It doesn't contain the complex business logic itself. It's more like a contract.
So where does the logic live then? The validation, the rules?
That all resides strictly within a dedicated command handler. That handler receives the command message, and it's responsible for the rich domain logic checking room availability, calculating complex pricing tiers, applying discounts, all that stuff. The handler is where your core business rules are enforced.
Got it. So the command side is this carefully guarded path for writes, holding all the complexity and validation. How does the query side manage to be so different, so fast and lightweight?
Because queries are basically the polar opposite. They are pure data retrieval operations. The golden rule is they never ever alter the state of the system. No side effects allowed.
Okay.
They're simple lookups designed to return data transfer objects, DTOs, or sometimes view models. These are data structures specifically shaped and optimized for whatever the UI or the calling client needs to display.
So no business logic, no validation stacks slowing things down.
None of that overhead.
Hmm.
They bypass the complex domain model entirely. They are built purely for speed and efficiency of data retrieval.
That vertical slicing seems incredibly powerful for maintainability. If I need to change a complex business rule for booking a room, I only need to look inside that specific command handler. I don't have to worry I'm accidentally breaking, say, the room display logic somewhere else.
Precisely. It enforces really clear boundaries. And as systems get genuinely complex, those boundaries are absolutely critical for keeping development sustainable and reducing cognitive load for the teams.
Okay, this is where it gets really interesting, I think. The separation isn't just in the application PERD. It can, and often does, extend right down to the database layer. This gives you some serious optimization power.
This is the big architectural leap, yeah. Let's trace the flow. A user action triggers a command. That command object goes to its handler. The handler executes all the complex domain logic, maybe interacts with the DDD aggregate.
We'll get to DDD aggregates in a bit.
Right, and then it persists the resulting state change using the right-side model. Now, for maximum data integrity, this right model might be, say, a nicely normalized relational database structure.
Okay, makes sense for rights, transactional safety.
Exactly. And for resilience, especially if you've got high traffic, that command processing might even happen asynchronously. Stick the command on a message queue, let a background worker handle it.
And the query pipeline, how does that contrast?
It completely bypasses all that right-side complexity. A user requests some data, maybe to view their order history. A query object is created, like get order history query, that goes to its own query handler. And here's the key. The query handler retrieves the data directly from a dedicated read model. It doesn't touch the write model or its database.
So this is the core flexibility of CQRS. These two models, write and read, don't have to be the same. They can live in different databases even.
Yes, exactly. That's the strategic advantage. You might use different data store technologies, each one optimized for its specific job.
Okay, hang on. So we could be talking about managing two totally separate databases. That sounds like it could double the infrastructure cost and, well, the maintenance headache. Why is that overhead actually worth it?
It's justified by the massive performance gain you can achieve, especially for complex reads. Think about generating a complicated report or displaying a user's dashboard with data pulled from many places.
Right, lots of joins usually.
Exactly.
Yeah.
If you had to query your normalized, right-optimized relational database for that, you might need, 10, 12 complex SQL joins to stitch all that data together just for display. That could take hundreds of milliseconds, maybe longer under load. The database engine is working hard.
And the read model avoids all that joining pain.
Precisely. Because you design the read model specifically for those queries. You might use, say, a denormalized NoSQL database, like a document store or a key value store.
Ah, okay.
The data needed for that dashboard view could be pre-calculated and stored together in one document. So the query handler just does a super fast lookup, maybe by user ID, and gets everything it needs in a single quick operation, often in milliseconds.
So you're essentially trading some infrastructure complexity and data synchronization effort for potentially huge improvements in read performance.
You got it. You optimize each data store for its specific purpose. Transactional integrity on the right side, blazing fast retrieval on the read side. And what's really cool is that CQRS doesn't usually live in a vacuum. It plays really nicely, synergistically, with other advanced architectural patterns.
Right, let's talk about those partnerships. Probably the most famous one is with domain-driven design, DDD. You mentioned aggregates earlier. How do CQRS and DDD fit together?
They're a natural fit, especially on the command side. CQRS provides the structural separation keeping reads away from the complex writes. DDD then provides the sophisticated modeling tools you need to actually manage that complexity within the command model.
Okay.
The DDD aggregate becomes the guardian of consistency for a specific part of your domain. Think of it as a cluster of related objects, like an order with its order lines, that must always be treated as a single unit to enforce business rules and invariance.
So the aggregate acts as the boundary for transactions.
Essentially, yes. Before any state change from a command gets fully committed, the aggregate ensures all its internal business rules are satisfied. It protects the system from getting into an invalid state. It provides that robust consistency that the CQRS right side needs.
Makes sense. And then there's event sourcing, VS. Combining CQRS with event sourcing seems to unlock some really powerful capabilities like auditing and replaying history.
Oh yeah, that's often seen as the ultimate CQRS power-up. When you use event sourcing, your write model fundamentally changes. Instead of storing the current state of your data...
Think of the current customer address.
Right. Instead of that, you store an immutable append-only log of every single state-changing event that has ever happened in the system. Customer registered, address changed, order placed, payment received. That stream of events becomes your single source of truth.
Okay, so the right side is just logging events. How does the query side get the data it needs then? How does it know the current address?
The CQRS read models are built from that event stream. There's a process, often called projection or building materialized views. You essentially run the stream of historical events through specific processors.
Like little calculators?
Sort of, yeah. Each processor listens for relevant events, address changed maybe, and updates a specific read model accordingly. So one projection might build a read model optimized for displaying customer details. Another might build one for order summaries.
Wow, okay, the big advantage there sounds like flexibility. If, say, a year down the line, the business needs a completely new kind of report or dashboard.
You don't touch the right side. You just write a new projection processor. You point it at the existing event log, maybe replay all the historical events through it, and boom, you have a brand new optimized read model ready to be queried.
Without impacting live transactions at all.
Exactly. Plus, you get a perfect audit trail of everything that ever happened and the ability to reconstruct the state of your system at any point in time. It's incredibly powerful.
And briefly, how does CQRS help in a microservices world?
It fits very naturally. CQRS facilitates independent scaling and resilience. Think about it. A microservice responsible for showing product catalogs, huge read load, maybe low write load, can scale out its read-optimized infrastructure completely independently.
From, say, the order processing service, which has critical write integrity needs, but maybe less read traffic.
Precisely. That separation reduces coupling between services and makes the whole system much more robust to failures in one part.
Okay, let's pivot slightly and talk about the strategic reasons why you'd take on the complexity of CQRS. What are the big wins that justify the initial investment? We've touched on performance, but let's nail down the core benefits.
Well, scalability is probably the biggest driver. As we discussed, if you have really lopsided workloads, think e-commerce with millions of product views versus relatively few purchases, that's a huge difference in read versus write load.
Like 100,000 reads for every write, potentially.
Easily. CQRS lets you scale the read side independently. You can throw cheap, horizontally scalable read databases or caches at the read problem without overwhelming your critical, perhaps more expensive, transactional write database. It's about efficient resource use at scale.
And beyond raw scaling, there are security and maintainability gains too, right?
Definitely. On the security front, you can apply much stricter, fine-grained access controls to the command side. Maybe only specific internal services are allowed to issue commands that change state, while the public-facing API only has access to the query side.
That makes sense. Limit the attack surface for state changes.
Exactly. And for maintainability, as we said, that vertical slicing really helps. Code bases become more predictable, it reduces the chance of unintended side effects, changing query logic won't break commands, and vice versa. It also facilitates parallel development. Different teams can work on the right side domain logic and the read side presentation optimization concurrently.
But, and this is important, CQRS isn't a silver bullet. It's not for every project. We have to be really clear about the costs and trade-offs. What are the main reasons someone might not choose CQRS?
The number one reason is complexity and the associated overhead. Let's be honest. CQRS is often total overkill for simple CR root applications where the read and write patterns are pretty similar and the business logic isn't too hairy.
Right.
You now have to manage at least two models, potentially two databases, figure out how to synchronize data between them if they're separate. It's a significant increase in initial development effort and ongoing maintenance complexity.
There's just more moving parts to worry about.
Absolutely.
Yeah.
And then there's the big one, the concept that often makes architects nervous: eventual consistency.
Ah, yes, the elephant in the room.
Yeah.
If the read and write stores are separate, they can't be updated instantaneously together, can they?
Not typically, especially if you're optimizing for performance and resilience using asynchronous updates like via that message queue we mentioned. There will inevitably be a null delay, maybe milliseconds, maybe longer depending on the system, between when a command successfully changes state on the right side
Like making a purchase.
and when that change is reflected in the read model you query to see your order history. The read model will be eventually consistent, but not necessarily immediately consistent.
And our source is stress. This delay isn't a bug. It's a conscious design choice.
It absolutely is. It's a trade-off. You are deliberately choosing to prioritize availability, resilience, and performance over immediate transactional consistency across the entire system view. The real challenge isn't the lag itself, but how you design your system, especially the UI, to handle it gracefully.
Yeah.
CQRS forces you to confront and manage eventual consistency explicitly.
So how do you handle that? If I just bought something, I kind of expect to see it right away in my order list. Showing potentially stale data seems risky.
It requires careful design, often involving engineering compensation patterns in the user interface. For instance, when the command to place order returns successfully to the UI, instead of immediately refreshing the order list by querying the potentially stale read model.
You do something else.
Yeah, the UI might optimistically update itself. It could show the order as processing or pending confirmation based on the command's success, maybe using data sent back directly from the command handler or just inferred. You display the intent or the acknowledged action rather than relying solely on the immediate state of the query database. This bridges the gap and manages user expectations during that brief consistency lag.
Okay, that makes sense. Manage expectations visually. Let's try and ground this a bit more. We've talked concepts, but how do developers actually implement CQRS in practice without drowning in boilerplate code for routing commands and queries?
Yeah, you definitely don't want to be writing manual switch statements everywhere. The most common approach relies heavily on the mediator pattern. In the .NET world, for example, libraries like Mediator are extremely popular for this.
Mediator, right. How does that help?
Well, the mediator, often exposed as an interface like iSender or iMediator, acts as a central dispatcher. Your application code doesn't need to know which specific class handles a particular command or query.
It just sends the message to the mediator.
Exactly. You create your placeholder command object, you pass it to the mediator's Zen method, and Mediator takes care of finding the registered placeholder command handler and invoking its handle method. It completely decouples the sender from the receiver.
And this is what enables that thin controller idea we see mentioned.
Precisely. Your API controllers become incredibly simple and clean. Their only job is to receive an incoming HTTP request, maybe pull data from the route or body, create the appropriate command or query object like getProductByIdQuery, and then immediately hand it off to the mediator.
So the controller has zero knowledge of business logic, database interactions, validation.
None whatsoever. It just acts as a translation layer from HTTP to the internal messaging system. All the real work happens in the handlers, which are nicely isolated and testable. You could wire it up manually, but the mediator library saves you a ton of repetitive wiring code.
Okay, wrapping things up then. What's the big takeaway for you, our listener? CQRS is clearly a powerful pattern for transforming potentially complex, tightly coupled applications into more flexible, scalable architectures.
But, and it's a big but, you absolutely must justify the added complexity it brings. It's not a free lunch. The decision framework really comes down to a few key questions for your specific context.
Right. So CQRS might be the right path for you if, one, your business logic is genuinely complex, making that single CRU model painful and unmanageable.
2, if your system experiences significant, really disproportionate differences between its read workloads and its write workloads, that scaling separation is a major benefit.
And 3, and this is crucial, if eventual consistency is an acceptable and manageable trade-off in your domain in return for those substantial gains in performance, scalability, and availability.
You have to be comfortable with and actively design for that slight lag between writes and reads showing up.
It really forces a shift in how you think about prioritizing speed versus absolute immediacy in system design, doesn't it?
It does. And it's worth remembering, as one source pointed out, eventual consistency isn't some weird artifact unique to CQRS. It's inherent in almost any distributed system at scale. Cache invalidation, database replication lag, it's everywhere. CQRS just makes you confront it head on, acknowledge it, and build mechanisms to handle it intentionally, rather than pretending it doesn't exist until it bites you. So think about the large-scale applications you use every single day, your social media feeds, massive e-commerce sites, streaming platforms. Are you, as a user, generally willing to accept a tiny, perhaps imperceptible delay in seeing the absolute latest update everywhere simultaneously in exchange for a much faster, more responsive, and more reliable overall experience?
That's a great question to ponder.
That intentional trade-off, choosing availability and performance, sometimes over strict, immediate consistency, that's really at the heart of designing robust, modern, distributed systems.